Greetings, mathematicians. We're going to be working through two different topic areas here. The first of which is how we can use calculus to be able to find lengths of curves that you really can't do with just basic geometry. And then that will unlock the ability for us to be able to find the surface area or the total area on the outside of some three-dimensional object when you take some portion of a curve and you revolve it 360 degrees or 2 pi radians around some axis of revolution. So let's dig in. It's going to be amazing. So what you see here is you see a polygon at the left and then a circle at the right. And the polygon, you would be able to easily find lengths or distances on it because they're all straight. So you could literally just put a ruler up against it, right? For the circle, can't really do that. But you do know that there's like that diameter times pi relationship that gives the circumference. You could use that to help you find the whole circumference or portions of the length around or whatever may have you, right? We don't have any geometry formulas that we can use to find lengths along a curve like this, and that's why we need calculus to figure out lengths of curves and such, right? So, to illustrate how we can do this, I'm just gonna chop off a portion of the curve. So how about if we just, I don't know, start it here and go to there. So we're just going to focus on this portion of the curve, and the idea here is that we want to try to be able to figure out what is the length of the curve on this little interval. Okay, so we're going to need to chop up our interval into little sections on the domain right here. So if this is like where A is at, and this is where B is at, and then we chop up A to B into, I don't know, let's say like 6 equal sections or something, right? So 1, 2, 3, 4, 5 tick marks and break it into 6, and we can call these maybe these numbers. How about? What we can do, at least geometrically, is we can kind of approximate the overall length of this red portion of the curve by finding y values that correspond to each of these partitions right here, and then um, connecting each of the y values in each of these partitions together to get a bunch of straight line segments. And then these straight line segments, let me just put in this lighter blue color, we would be able to find those distances, and they would approximate and give us a pretty good guesstimate of what the arc length would be. So exactly for this segment that I just put in purple right here, so it stands out a little bit, it'd be pretty easy to figure out the length because you could figure out what this vertical distance is right here, which I might call change in y. And then this horizontal distance right here, which I'll change in x. And yeah, you could easily find that distance d because you could just use the Pythagorean theorem, right? Because the distance would be the square root of the change in x squared plus the change in y squared, right? And then you could do a similar thing to figure out that length, and this length, and this length, and that length, and that length, right? And then you just add them all together. So with that all in mind, then let's try to add them all together and see what would happen. So, in general, whenever we're talking about arc length, most people use the letter S to represent the length of some portion of a curve or an arc. So that's what I'm going to use to represent the length of an arc, is that lowercase s. So our arc length S that I put in that red color would really just be the adding up of, I guess, 6 different little segments that I originally put in that lighter blue color, whose length would all be of the form square root of change in x squared plus change in y squared. But then for each individual line segment, the change in x and change in y is different every time. So we would have to label and index these this is the change in x sub I and change in y sub I. So it's for each interval, right? Okay, so then we just want to take this expression right here and do a little manipulating with it, and we're going to come up with what the arc length formula is here. So what I want to try to do first of all is I just want to be able to replace the change in y with something a little bit different. So what we need to use here is just like note that we know that the derivative of a function at like some x sub I point is really just basically like the change in y sub I over the change in x sub I, because like the derivative of a point tells you the slope of a tangent line. So of course it should be like the change in y over the change in x, right? So if I just take that identity and I get the change in y sub I alone, I just have to multiply by change in x sub I to cancel it out, and then do the same thing right here, right? So then this quantity right here is equal to delta y sub I, which then can actually replace that right there, because that is delta y sub I, right? So by replacement then, we're going to get this. Delta x sub I squared plus, and then now we're going to square this new thing of delta x sub I and f prime at x sub I, right? Okay. And then with this now, we're just doing a little bit of algebra. So you should all see that this term and this term, they both have delta x sub I and actually squared. So I'm going to do some factoring in that square root and factor out delta x sub I squared from both of the terms. So it would distribute to a 1 first, because in this term, that's all you have. It's just delta x sub I squared. And then plus, and then once you take the delta x sub I squared out of there, you're left with just f prime of x sub I squared right there. And then more algebra is that because you've got this and this right here multiplying under a square root, whenever you have a square root of a product, it's the same thing as product of square roots. So you could split it into two separate square roots, multiplying. And then I'm going to do another step when I do so, and the fact that then once you have this part in a separate square root, because then you're going to have something squared under a square root, then it just makes it only delta x sub I, but then this right here is stuck under the square root. Cool. All right, so technically right now we're only adding up like 6 little line segments. So what we really want to do a better job to approximate is to chop up this interval into even smaller sections so that then each little line segment gets more and more accurate and we get closer to the actual arc length, right? So what we really want to do then is instead of having like 6 of these guys is we want to have n of them, but then make n limit towards infinity, right? And this is like basically just the definition of a definite integral right here, because you've got a change in x right here, and then you've just got like a function right here. So it's kind of like your width times times like a height sort of deal, right, from the definite integral stuff. So it just ends up being an integral of that function, the square root thing. So this is literally just an integral, and it's going to go from a to b, because that's how I like set this interval up right here, of the function where we have 1 plus the derivative at x, all squared right there under the square root, and then dx. Yeah, it's that little friend right there that gives you then the arc length of the curve from A to B, which is pretty nifty, right? So the only like thing that's really major that allows you to use the arc length of the curve is you just got to make sure that um, you have a continuous curve, because otherwise if there was a discontinuity, like you're not finding lengths where it's discontinuous, right? So as long as it's continuous on some interval a to b, okay, then you can say that the arc length, which we'll denote as s of f on a to b, is given by the quantity s equals integral from a to b of the square root of 1 plus the derivative of the function at x all squared dx. Okay. So with that then, let's apply this in a relatively straightforward example to begin with right here. So we want to take the y equals x to the 3/2 curve right there and figure out the arc length of it on the interval of this domain of 0 to 4, right? So you're just finding what is the length of that curve right there from 0 to 4. So exactly as this picture, right? Cool. So arc length is integral from 0 to 4 then of the square root of the number 1 plus, and then what we need is we need the derivative squared. So since we know that y is equal to x to the 3 halves. That would mean that dy dx, or the derivative, right, is going to equal 3 halves x to the 1 half, or 3 halves squared of x, right, just by power rule and differentiating that. And then we need to actually square that as well. So then dy dx squared would be 3 halves squared of x squared, which 3 halves times 3 halves is 9/4, and square root of x times square root of x is x. So that's what we need to have right here is 9/4 x. And then we need the dx there. So this is literally all that we need to like integrate to get this all figured out. So if you just like let your u be the 1 plus 9/4 x, then you know that your du will be 9/4 dx. But there's really like no 9/4 in this to substitute for, so you just need to substitute for a dx. So multiply by the reciprocal, then you'll have 4/9 du is equal to dx. So now we'll just be integrating the square root of u, because I let all of 1 plus 9/4 x be my u. And then we're just replacing the dx with a 4/9. Okay. You could get new limits for your u, I guess, right? So I guess when x is 4, then u is going to be 1 plus 9/4 times 4, which would be 10. And then when x is 0, then u would be 1 plus 9/4 of 0, which is 1. So the new limits would be from 1 to 10 then. Cool. So then we just need to take 4/9 and then multiply it by the difference of plugging in 10 and 1 into 2/3 u to the 3 halves, which is the antiderivative of that. It should be 4/9 of, if we plug in 10, we plug in 1, we get some crazy stuff here. So if you plug in 10, you're going to square root it, but then cubic. So the square root of 10 cubed would be 10 root 10. But then we have to multiply that by 2/3 as well. So it'll be 20/3 root 10. And then this is just minus 2/3. And then that whole thing needs to be multiplied by 4/9 as well, which makes it become 80 square root 10 over 27 minus 8 over 27. And it's like good enough, right? So there you have it. That would be the length of that portion of the curve, right? We want to take a look at another example of just simply finding arc length for a curve over an interval. So here the function is y equals 1/8 x squared minus natural log of x, and we're going to find the arc length on the interval between 1 and e on the x-axis. So when we do this, because the limits of integration are on the x-axis, then we'll just do this with respect to x and go from 1 to e. And then arc length is square root of 1 plus, and then we're going to need the derivative squared. So up here, I'm going to find the derivative first, dy dx. So we're going to bring the 2 down, so it'll be 2/8 x, or 1/4 when you reduce it. So 1/4 x, and then natural log x's derivative is 1/x. So there's dy dx. And then we just square that. So dy dx squared. So since 1/4 x minus 1 over x is like a binomial, you'll have to FOIL that. So you'll do 1/4 x times 1/4 x, which is 1/16 x squared. And then you'll do 1/4 x times negative 1 over x twice. So it'll be like this times 2. And then that x and x cancel because the first x is on top, second x is on bottom. So you just get 2 times 1 times negative 2, so negative 2 over 4. This is just negative half. Okay. So minus half, and then the last part of the FOIL would be just doing the negative 1 over x times itself, which would be positive, because negative times a negative, and 1 over x squared. Cool, cool, cool. So then that's what we can put in right here is 1/16 x squared minus half, and then plus 1 over x squared underneath the square root, like we see right there. And then that's gorgeous. We can simplify by putting together the negative 1/2 and 1, combining them, just makes it positive half. So we get the square root then of 1/16 x squared plus 1/2, and then plus 1 over x squared. Okay, so this kind of looks like a not very pretty integral, right? Because you got all this stuff with x underneath, and then you like maybe pick it as a u, but then you wouldn't like have anything that's close to your du multiplying with it. But there's actually some really nice algebra that happens inside of this right here, where that we can actually factor the inside of this square root. So we do want to choose 1/4 x to go at the beginning of each of these factors right here. Because those would multiply to equal 1/16 x squared. And then we also do want to choose 1 over x to go at the end of each of these right here, because those would multiply to equal 1 over x squared. And then it's just so convenient that when you do this times that, the x's cancel, so it's just plus 1/4. And same thing right there, you get plus 1/4, which is plus 1/2 overall, which is exactly what we want. So, and that turns into that. And then because those two factors are literally the same, then you can just write it as that squared underneath a square root, which makes it all the more beautiful because then square rooting something that's squared cancels it out. And then we get integral from 1 to e of 1/4 x plus 1 over x dx, which is a kind of pretty simple, straightforward integral to find. So if we have to differentiate the 1/4 x, you have to increase the exponent to a 2 and then put it over 2, so it becomes 1/8. And then this will be plus natural log of x. And just evaluate that from 1 to e. So plug in the e first, and you get 1/8 e squared plus natural log absolute value e. Plug in 1, so 1/8 1 squared plus natural log of absolute value 1, which would be e squared over 8, and natural log of e is 1, and then minus the quantity of 1/8 times 1 squared is just 1/8 plus 0. Yeah, so it just ends up being like e squared over 8, and then plus 1 minus 1/8, but 1 minus 1/8 is 7/8. So like you basically just get e squared plus 7 all over 8 as the arc length there then. When we learned about the fundamental theorem of calculus, we learned about how we could accumulate areas starting at some particular number. So what I mean by that is if you have some sort of a curve, I'll call f, and you start at some number a, and then you start accumulating all of the area between the curve and the x-axis, all the way up until some number that you want to choose to stop at. And so that number we actually really want to choose as our variable that I will call x. So we can actually write a function of x, so capital F of x, where we would integrate from a to x, and that's our variable, and then it would be of the function f, but then we'd have to like think of f as some like dummy variable, so like f of t dt, so it's like a different variable than x. And that would be like a function to accumulate area starting at a all the way up until we get to x, right? So we can think of a similar sort of thing for arc length in terms of how much length we have accumulated so far on a curve from some point A up until x. And then we would call the arc length function. So in like a picture, what that would look like is if this is where A is at, and then you have your curve f right here that you're going to accumulate arc length at. So you'd start here when x is a, and then go until whenever, and stop like once you get to x, right? So we could actually define a function that I will call s of x as an arc length function that would really be integrating from a up until you get to x, and then we'd have to do like the arc length integrand that we would need, so the square root of 1 plus, and then we need the derivative, but then I want it of like the dummy variable, so like t all squared, and then dt. And then that would be like a way to talk about how you could accumulate arc length up until you get to x, right? So it is a legit thing that we call the arc length function. So to be able to accumulate arc length up into a point x, it's just literally what I gave to you right there. And then I want to make some further comments about some of the things that you're seeing because I want you to really, really strongly connect what you're seeing about arc length to some prior things that we've learned about. So since we know that the arc length function s of x is equal to the integral from a to x of the square root of 1 plus f prime of t all squared dt. What I'm going to do to this is I'm going to go ahead and I'm going to differentiate with respect to x to both sides right here. So on the left-hand side, you just get s prime of x. And then what we're actually doing on the right-hand side there is we're differentiating in integral. And because the integral goes from a up until a variable x, then x can actually get plugged in for the t in the integrand. And so you just get only then the square root of 1 plus f prime of x squared, because differentiating the integral just like does everything away, right? Now, I'm going to go ahead and then take this right here, and I'm going to square both sides. So now we get ds dx all squared. I just wrote s prime of x differently. It's still ds dx, right? Because it's the derivative of s with respect to x. And then when I squared the other side, the square root's going to go away. So then we just get 1 plus, and then that would be technically like kind of like dy dx squared, because the derivative would be like dy dx, and it's squared, right? So we would get that identity. And then I'm going to replace the 1, and I'm going to replace it with dx squared, because dx over dx would just be 1, right? So we get this little handy-dandy identity that you see here. And then you'll notice that like all the denominators are the same, so you could just like multiply both sides by dx squared, and then it just like clears out the denominators, and so then you just get this identity that ds all squared is equal to dx squared plus dy squared. And you think about like what that means. That means that, oh, hey, so like the change in the arc length squared is equal to the change in x squared plus the change in y squared. Like, that's basically just the Pythagorean theorem, right? And that's where the arc length came from, okay? I just want you to be able to see that relationship and just understand that at the core, that's really what's happening, right? And it's just that fact that we're limiting towards infinity that makes the magic happen for calculus, right? All right, so I want you to see an example here now where we can do arc length, but also be able to integrate with respect to integration limits that are on the y-axis. So here, we're going to set up an integral that defines the arc length of the curve that is defined by x equals natural log of cosine y on the interval 0 less than or equal to y less than or equal to pi over 4. Yeah, so basically just from 0 to pi over 4. So pi over 4 would be like a little bit less than 1. So we're only really looking at just a very small portion of the curve, I guess, like right there, right? Um, yeah, so since the function is already like solved explicitly for x in terms of y, then we don't really have a lot of work to do other than the fact that we do need to figure out what the derivative would be. So we need to figure out what dx dy would be first of all, and then square it. So dx dy, we have natural log of cosine of y. So I have to do the derivative of the outer function, which would be 1 over cosine y, and then multiply it by the derivative of the inside, which would be negative sine y. Okay. But then it ends up being negative sine over cosine, which we know is negative tangent. So yeah, negative tangent y is just going to be the derivative. So then we would know that the derivative dx dy all squared would be negative tangent y squared. Negative times a negative is a positive, so it's just going to be tangent squared y. So then we can get the arc length. So arc length as a function of y will be an integral from these limits of 0 to pi over 4 of the square root of 1 plus tangent squared y was our derivative squared, and then with respect to y. Okay. Now we could do some interesting, really cool things with this. So one of the Pythagorean identities that we know of is that 1 plus tangent squared is equal to secant squared, actually. So it's just the square root of secant squared dy then that we're integrating. And then when you square root something to square in, it just becomes secant. And then if we did the fancy dancy substitutions, we could multiply this by like secant plus tangent over secant plus tangent and do all like the work of that. You get like natural log of absolute value secant y plus tangent y. That then you could evaluate from 0 to pi over 4 and then like, come up with your answer, right? I'll just skip over the math of that. You know how to do that. Just the biggest thing that you want to see there is just how you could set that up in terms of y. And then just another quick little one right here is we're asked to set up an integral that is defining the arc length of the graph y to the fifth equals x plus 2y between the 2 points 1, -1 and 28, 2. Um, so there's like a couple ways that we could do this, I guess. We could do it either in terms of x or we could do it in terms of y. But when you look at the picture, you'll see that it's kind of a little bit of a problem. That if we go from, so 1, -1 would be right here, actually. And then 28, 2 is it's like way over there, I guess. So we're looking at this curve and it's going to go all the way until you get to 28, 2, right? It would be a huge problem to actually integrate from like this x coordinate to this x coordinate because it's not a function. It fails the vertical line test. But if you look at it sideways, then it's like would pass the vertical line test if you look at it sideways, but like it just passes the horizontal line test. So it's 1-to-1, right? So a better idea would be to actually integrate it this way because then it's like a function if you tilt your head sideways that way. So we'd actually like really need to do it that way, which then means that we would want to do an integral from -1 to 2, basically what those y numbers are, right? And so then we'd have to figure out everything in terms of y for this integral, right? So it'd be with respect to y, we do a square root of 1 plus, and then we need to like get the derivative of our function, right? So since this is your equation right here, well, right now it's not like explicitly written, so we need to get the x alone, and so you'd have to, I guess, just subtract the 2y, and so x would equal y to the fifth minus 2y, right? And then you can get your derivative. So dx dy would be 5y to the fourth minus 2. And then you have to square that. So dx dy all squared would be 25y to the eighth. And then you get minus 10y to the fourth twice, so minus 20y to the fourth, and then plus 4. And then that's what you can substitute in right here to add with the 1 underneath the square root. Okay. Yeah. And then, like, proceeding from there, you'd have to do some crazier stuff that we haven't really talked about in terms of integrating there. So we're just going to leave it right there. All of my instructions say there, anyways, is just to set up an integral that would figure out the arc length. So, voila, we did. So the big thing to understand there is just that, sometimes that it really is better to integrate certain things with respect to y versus x. And that holds true here for arc length, but we've also seen that pop up like when we try to find areas. And the same thing's true for like volumes and surface areas and such. Okay. We're going to spend the remainder of our time working to compute surface area for three-dimensional solids that we produce by revolving some portion of a curve 360 degrees around an axis of rotation. So pictorially what this looks like is what you're seeing exemplified right here, how we could take like an arc like this right here and just spin it 360 degrees around some axis of rotation. And then you get some solid like you're seeing pictured right here that we can pretty easily compute the surface area for. Now, when we find the surface area for this, we're not really going to be able to find the surface area of like the sides of this, where you have those like circular bases. It's really just going to be the surface area going around right here. And how we find this is just like how you would find like the surface area of like just like a normal cylinder, like the round part of it. How really what you would need to know is just what is the length of this actual arc right here. And then once you know the length of that arc, since you know that you're going to spin it around 360 degrees, you want to take that arc length and multiply it by 2 pi, just like how you would want to do that for like the circumference of a circle, right? When you're spinning something around. But what that is all relative to is really just like the radius of rotation at any given point. So I just marked right there one of the radii, right? Because the radii is always going to be different at different points. Now that radius is always basically just going to be the y value of the function because it's just the distance between the function and the x-axis always, right? So it's those critical pieces that really completely dictate how you're going to get the surface area for a solid of revolution. So, yeah, for any solid of revolution, then the surface area is just using all those different things. So you're integrating from A to B along the x-axis, just like how this picture had that right here, because the idea is you're really just taking a bunch of like circular cross sections and then just sliding that from A to B and looking at like the circumference of those circular cross sections. So we'll integrate from A to B then of 2 pi, which can just be a constant in front, since constants always get pulled in front if they're multiplying with the function, of f of x, and then multiplied by the square root of 1 plus the derivative of f, all squared there, dx. Yeah. So like this part right here is really just what you have from arc length, right? And we need that. And then we also have this friend right here, which is really just telling you like what is the radius of your rotation that then gets multiplied by this guy right here, which is just like the angle of rotation. Yeah, and you have your integration limits there as well, but that's basically kind of all you need to figure it all out. So let's apply this, right? I'm going to do this example in a couple different ways because it just kind of shows you very niftily how you can actually figure out surface area integrating with different limits with respect to x and with respect to y. Um, so like with this problem as it's given, how we want to try to determine the surface area of a solid formed by revolving the curve y equals cube root of 4x about the y-axis over the interval from 1 to 3 and y. It would make most sense to just do this in terms of y since you're revolving this over the y-axis. The interval 1 to 3. And it's pretty easy to solve for that to get x alone in terms of y. So that would make the most sense, right? So for surface area, then we want this to be 2 pi, and we'll integrate from 1 to 3 then, but then it's got to be an integral that's with respect to y, right? So what we're going to need right here is we need x equals whatever in terms of y, the function for that. So this equation right here, we're going to need to solve for x alone. So let's cube both sides. So we get y to the third equals 4x. And then you can divide both sides by 4. So 1/4 y to the third is equal to x. And that's what we're going to need to put right here. So y to the third over 4 right there. That's going to be your, your function for x in terms of y. And then we need to multiply that by the square root of 1 plus the derivative of that squared. So then we're going to need to take this guy right here and get the derivative of that. So like dx dy, which would just be using power rule. So you bring the 3 down and become 3/4 y squared. But then that's going to have to get squared. So we get what dx dy squared is, then 3/4 times 3/4 is 9/16, and y squared is y to the fourth. So that's what we're going to need right here then is 9/16, y to the fourth like that. Okay, beautiful. So then we can integrate this and come up with an answer. It's not super crazy, but it's not the nicest of answer that we're going to get right here. So 2 pi, we'll have to do some u substitution, I guess. So u we're going to let be the quantity that's inside the square root, so 1 plus 9/16 y to the fourth. And then du is going to be, you can bring the 4 in front, so it'd be 36/16 y to the third, which then you can reduce 36/16 because both are divisible by 4, which makes it 9/4 y to the third. Which is pretty cool because then like you want to replace the 4 bit down there and the dy and the y to the third. You just don't like really need the 9, so you could make 1/9 du equal to just y to the third over 4. I need the dy's in here too, dy, right? And then, yeah, so then you just do like an integral that has the square root of your u, and then 1/9 du. So it'll just be 2 pi over 9 then, and then once we find the antiderivative, it'll be 2/3 u to the 3/2. Um, yeah, and then I guess you could change your integration limits if you wanted to. So what was our u? Our u was here, and so when y is 1, u would become 1 plus 9/16 times 1 to the 4th, which would be just like 16/16 plus 9/16. So 25/16 you could change to your new lower limit. And then when y was 3 as your upper limit, you would become 1 plus 9/16 of 3 to the 4th, which would be 1 plus 9/16 times 81. That becomes a little bit more involved. It comes out to be like 745/16, I believe. Um, yeah, so just a little bit of crazy stuff. So, yeah, you just do 2 pi over 9, and then we have to plug in 745/16 first. So do 2/3, 745/16, so the 3/2, and then subtract and plug in 25/16 to get raised to the 3/2 right there. And then you just like, you're gonna need to figure that stuff all out and just like do math. I'm gonna stop it right there. So you just like plug in a calculator and get a decimal answer, and I guess that'd be good enough, right? Yeah, so then I just want to illustrate the same problem, in that you can do this with respect to x if you so wanted to do so. So, like how we were trying to take this portion of the curve between 1 and 3. So, we're really talking about like this guy right here. Um, yeah, so that portion of the curve we could actually revolve around the x-axis. Now you'd actually need to like figure out like what x numbers this is like actually corresponding to. So I guess since it's like when y is 1 to y is 3, you'd have to plug in 1 for y and then solve for x. So cube both sides and then divide by 4. So it's when x is equal to 1/4. And then you can set it equal to 3 for y. And then cube both sides. So 27 equals 4x. And then divide by 4. So 6.75 is equal to x. So you could actually do an integral from 0.25 to 6.75 then. And get surface area is 2 pi times that integral. And then you need f of x, which is the cube root of 4x. And then the square root of the 1 plus the derivative dx. So yeah, you could just differentiate that. So the derivative would be bring the 1/3 down and then make 4x be to the negative 2/3 now. And then do chain rule and multiply by 4. So just more simply, it would be like 4/3, 4x to the negative 2/3. So that would be the derivative, but then you'd have to square the derivative and get 16/9. And then by properties of exponents, it'd be 4x all to the negative 4/3 then. So yeah, then that thing is going to have to get plugged in right here. That's 16/9. 4x to the negative 4/3 right there. And then you just like do some math. And then you're just going to get the same answer as what we got before. Whatever it would have been as like basically a decimal answer. Okay. All right. So I just want to do like one more just very specific problem. And this one I'm only just going to set it up and I'm not going to evaluate it all of the way, even though it wouldn't be super crazy, but it's the easiest thing in the world, I guess. Yeah, so here we want to set up the integral to find the surface area of the solid formed by revolving the indicated curve y equals e to the x plus e to the negative x over 4 about the x-axis and the interval from 0 to half on x, right? So that's revolving this around the x-axis, and we've got integral limits from 0 to half on the x-axis. Then this thing's going to be with respect to x. So in fact, then for your f of x, you can just have e to the x plus e to the negative x over 4. And then you need the square root of 1 plus, and then you need your derivative squared, right? So let's find the derivative. So dy dx is going to be, well, e to the x, and then e to the negative x is e to the negative x, but then because of chain rule, you have to multiply the derivative of negative x, which is negative 1, so it becomes minus e to the negative x over 4 then. And then you have to square that. So then dy dx squared will be, so e to the x times e to the x is going to be e to the 2x. And then you're going to have to do e to the x times negative e to the negative x over 4, and that's going to happen twice. The exponents add and become just 0, so it becomes negative 2 over 4 times 1, so just negative half, I guess. And then finally the last times the last would be e to the negative x over 4 squared. So it'd be e to the negative 2x over 16. So plus, because the negative term's a negative, e to the negative 2x over 16. So then that quantity is going to get plugged in here. So plus e to the 2x minus half plus e to the negative 2x over 16. Okay, and then that's like, and then we need the integral limits, 0 to half. And then we also need 2 pi in front. And then that would be the finished, like, set up the integral at least for how you, like, figure out the surface area of it. Okay? All right. So with that then, we'll end with just kind of one last little nifty example that will show you how we could actually derive surface area for a sphere of radius r. So you should recall from geometry that surface area for a sphere is just going to be 4 pi r squared. Yeah, so we could actually figure that out pretty easily. So what I'm going to do here is on the coordinate plane, I'm going to sketch out a semicircle that has a radius of, let's just say, like capital R. So this right here is going to be located then at capital R, and this right here is going to be located at negative R. And then note that this semicircle would have an equation of y equals the square root of capital R squared minus x squared, just from what we know about circle equations, right? Like x squared plus y squared equals the radius squared. So then surface area, by the integral definition of it, would be 2 pi, and we'd want to integrate from, I guess, negative r to r of our function for this semicircle, which would be the square root of capital R squared minus x squared, and then the square root of 1 plus, and then we need the derivative of our function squared. So I'm going to do a little bit of side work for this right here. So we know that y is equal to the square root of r squared minus x squared. So then dy dx would be the derivative of that, which would be 1 over 2 root, but then we'd have to do chain rule and multiply by the derivative of the inside of that, which would be negative 2x, right? So then I guess we could bring the negative 2x up to the top here to multiply with 1, and then you could like cancel out the 2, so it's really just negative 2 over that. And then we'll have to square this to get dy dx squared, right? Which then makes it just become x squared over r squared minus x squared. Yeah, beautiful. So then we can substitute that in right here, because we need the derivative squared for this part. dx. Okay, yeah, looks beautiful. Now, just to make this come out a little bit nicer then, I want to change what this 1 is right here. So we did have the number 1, but I'm going to write it as r squared minus x squared over r squared minus x squared, so that it's still equal to 1, and then it forces it to like have a common denominator with the other fraction that's done to the square root right there. So then the minus x squared and x squared, it's going to cancel right there. So then you just get the square root of r squared over r squared minus x squared right there. And then we know that by properties of radicals, that you could split up a quotient that's under a radical into separate radicals that are divided. So it'd be the square root of r squared on top over the square root of r squared minus x squared there, multiplied by the square root of r squared minus x squared in front of that. And then like these guys here just like cancel out. And then right here, you have the square root of something squared, so then it just ends up being like r. So it's going to be the integral of 2 pi r, integral from negative r to r of 1 dx. I could pull the r in front because r is just like a known number, right? X is what our variable is, so the r could have been pulled in front. And then the antiderivative of 1 is just x, and then we're going to evaluate x between negative r, and then multiply it by 2 pi r, which makes it become 2 pi r, and then you can plug in r for x, and then plug in negative r for x, and subtract. So that makes it become 2 pi r times 2r, and that, yeah, comes out to be 4 pi r squared, which is exactly what the surface area is for a sphere, right? So it just kind of shows you how, like, cool that integral definition is and how we can come up with surface area for lots of different various solids that we could like revolve around an axis.